is Unit 3. What we're going to start out doing, so everybody up here, what we're going to start out doing is talking about extrema. When I say extrema, I'm talking about minimums and maximums. That's better color. Minimums and maximums. Okay? Anytime you see this capital I, it means an interval. Okay, we're not going to really be talking about minimums and maximums of an entire function, just usually a part of the function. And f of c, okay, c here is an x value. F of c is the minimum when that point is the lowest point. That should make sense. The minimum is the lowest point. If f of c is greater than or equal to f of x, then f of c is at the highest point. Now, how long have you been doing minimums and maximums? Yeah, a long time. All right, so some of this is going to be really old, and some of it's just going to be putting some new vocabulary with some old concepts. So minimum and maximum of a function are the extreme values, or we're going to call them the extrema of the function on the interval. We're also going to use this term absolute minimum or absolute maximum. When I say something is absolute, what's implied in that?
Indefinite.
For sure, positively, definitely. There's no other answer. It's that thing, okay? We're going to talk later about relative extrema, and I'm going to explain the difference. But absolute min and max are the absolute lowest or highest point on that particular section of the graph. So when this is find the absolute extrema, part A, this is a parabola. Normally we would see arrows on this parabola. Here we don't, okay? But the minimum, the absolute minimum, is still right down here. I'm going to go ahead and write it as coordinates of a point. I'm going to say this several times during the lesson, but when you say the minimum is at 0, 1, the 0 is the x value telling you where the minimum is. The 1, though, is the really important part of what is the minimum. 1 is the absolute lowest y value of any of these points. Okay? Where would the absolute max be? 2, 5, right here, okay? Absolute max, and that's going to be at 2, 5. And again, 5 is the highest y value, and 2 is more or less where that's occurring. Okay, so when you write, see the absolute max is at 2, 5. 5 is the maximum number, 2 is where that's happening. All right, what if this was just like a regular parabola, and we weren't talking about an interval, and there were arrows at the end? What would the absolute max be in that case? Infinity, okay? Or we'd say there is none, all right? So that's fine, all right? And then we get to B, and they put, this is now an open interval, okay? A was called a closed interval because we included the endpoints. Now, A, we have open endpoints. One of these two things will not be affected by this. Which one?
Minimum.
The minimum, okay? This is still 0, 1. It's still the absolute minimum. Okay? However, the maximum now is not at 2, 5. If I just said, I want you to give me a number of where the maximum is, what would you say? Around 5, so like 4.999999. And what's a word we use for that? Limit, okay? So it kind of brings it back. For right now, though, all I really want you to know is that point right there is not the absolute maximum. Okay, 2, 5, not the absolute maximum because it's not a point. It's a hole. Okay, so then we get to C, and in this case, we kind of messed around with the minimum. In that there's a hole at the minimum, there's a point above it. So what's the deal with the minimum? Is the absolute minimum still 0, 1?
No.
No. So I just want you to write not the absolute minimum. Now we could put some, we could use limit, and we could do a lot of things to say, well, what is the minimum? But I just want you to see that when there's a hole there, that's not the absolute minimum. Now, if this point, which was here, it was kind of moved above, if this point had actually been below, we would have a minimum then, all right? But we don't here. All right, and then the absolute max, that's still 2, 5, okay? So that didn't change on this one. Yes?
So if the point is below the line, and let's say it's not continuous, then would that still count as the minimum?
So, yes. When you mess with continuity, though, you really mess up the extrema. And I'm glad you asked that because that really gets into this next part. Okay, anytime you don't have continuity, you really can't make all the same assumptions. And so we're really going to be dealing with continuous functions for that reason. And so that's kind of what this sentence here says. Here's a new theorem, the extreme value theorem. Anytime a theorem has an actual name rather than a number, that means it's something we're really going to talk about. And we are going to do a theorem write-up. We're not going to do it today about this. So today I just really want you to understand what is the extreme value theorem. It has to do with extreme values, all right? But get this. If f is continuous, that has to be true in order to even talk about extreme value theorem. So out of A, B, and C, which one of those can we not even mention extreme value theorem? Out of these three? C. C is not continuous. You can't even talk about extreme value theorem. Okay? So then it says closed interval, A to B. This means that you have endpoints, not open circles. So which one would be out?
B.
B. Okay. So B and C, they have nothing to do with extreme value theorem. Only this one right here. Okay? If both of those things are true, though, then we can be sure that f has a minimum and a maximum on the interval. So I want you to imagine you have a point over here, you have a point over here. I don't really care how high or low. As long as you're continuous, it doesn't matter how low or how high you go, you are going to have a maximum and a minimum. It has to happen, right? Anybody think of a weird case? Straight line? In which case, they're all the values, all the y values are the same. So they kind of all tie for max and min, and you can have ties. You can have 2 points. I didn't really draw this here, but let's say these points were actually the same height. You could have 2 points be the max because they have the same y value. Same with min. Okay, another thing that can happen is that, okay, so here's my absolute max, and here's my absolute min. Well, we have all these other little mins and maxes. This is what we call relative extrema. So the word relative here, I don't want you to think of your relative like people you're related to. I want you to think about if a Doberman Pinscher walked in this room and I said, wow, that's a big dog. Is it a big dog? Is a Doberman Pinscher big compared to a Min Pin? Yeah, it is quite a bit bigger than a Min Pin. But what is it not big compared to? Great Dane, or there's other dogs too. So I would say, you'd say that's relative. This is the kind of relative I'm talking about. Mins and maxes, if you just look at just that one spot, it looks like it's a min or a max. But if it's not the absolute min or max, we call that relative. Okay? So we have this open interval, basically a piece of the graph. So that little piece right there, that would show us where the relative max is. But it's obviously not the absolute max. That's just the vocabulary I want you to get down. All right. Now, looking at this graph right here, if these endpoints, if these were actual points, they would represent the absolute max and min, okay? I'm not going to do that, though. I'm going to go ahead and put arrows on this, just for fun. So what is the absolute max now? There isn't one. And what's the absolute min? There isn't one. Okay, this is a cubic function. Do you think a cubic function could ever have a max or a min? If we're talking about the whole cubic function, there's never going to be an absolute max or min. Now, if we're talking about a piece of it, then of course there will be. And here, the real question I want to get at is the relative extrema. Okay, polynomials have lots of relative extrema. Sometimes they have absolute and sometimes they don't. All right, so where would you say is the relative min?
-4.
Yeah, -4 is the lowest y value in its section. And so we would call this a relative min. And we're going to go ahead and use both numbers here. However, I don't know why I wrote 5. That's weird. -4. I really want to stress, though, that the -4 is the minimum y value And the 2 is really just saying, where is it happening? It's my x value. So we use the coordinates of the points that the y value is the lowest y value in its area, the relative min x value, though, is just where it's happening. Okay, then 0, 0, we would call that the relative max. Okay, it can happen that a relative max is the absolute max. It just didn't happen in this problem. Okay, so this is just looking at vocabulary, forwards, backwards, sideways, upside down, all that. Okay, so let's look at this next part. And let's work smarter, not harder on this. So this says, find the value of the derivative at the indicated relative extrema. We saw this in the last chapter. I would say, find the value of the derivative at 3, 2. And what would you do? You'd find the derivative algebraically, and then what would you plug in? Would I plug in the 3 or the 2? The 3. In this problem, I would only be plugging in the 3 because this is in terms of x. In the problems where we had implicit differentiation, we would have to plug in both. Okay, but because I gave you the graph, and because I'm telling you that this is a relative extrema, I can actually get out of doing the derivative. All right, derivative. What does the derivative represent graphically? Slope of tangent line. So slope of tan line. All right, so let's think about this. 3, 2. They're telling us that's the max. What type of tangent line is occurring there? Yeah, horizontal, right? All lines are straight. I love that, straight lines. All lines are straight. So this is a horizontal. Now, what is the slope of a horizontal line? 0. So at this relative extrema, in this case relative max, the derivative is 0. I mean, that is your answer. That's the value of the derivative. Now, if you had done this algebraically, you can get the same answer. You just need to do all of that work to get it. Okay? A lot of extra work. All right, so I want to draw, before we go to B, I want to draw another relative max. It's just a simple parabola. Okay, and I say I want you to find the value of the derivative at this relative max. What would that value be? 0. What if I change it to a min? This is still a parabola. It's still 0. So do you think that the derivative is always 0 at relative extrema? Maxes and mins. Okay, I'm not going to confirm or deny that, but let's go to B. Okay, B, absolute value. 0, 0 is the relative min and the absolute min. But what's the derivative? Right here. The derivative is, we'd call it undefined, right? Why? Yeah, because they're not differentiable. So anytime you have that sharp turn, there's no derivative there. That's because your tangent line could look like this, it could look like this, it could look like this. The tangent line just means it goes through the curve at one point. Right? So this is undefined. So yeah, 0 is what's going to happen most of the time, but sometimes when you have a cusp, you're going to have a derivative that's undefined. Okay, we can even see how this works in trig functions. Here's the sine curve. All right, and it looks like it's just 1.5 cycles. Right here at the max, what's the derivative? 0. Right here at the min, 0. How many maxes and mins does the sine curve have without bound? Like if you just draw the sine curve and there's no interval, how many maxes and mins are you going to have? Infinitely many. Okay, so probably when we get to deal with trig, we're going to have an interval because otherwise you just have infinitely many answers. All right? Okay, let's look at the next page. So this is going to recap what we just said, which is at a relative extremum, this is like singular here, the derivative is either this or this. What are our two options? 0 or undefined. That's always going to happen. Okay, so if the derivative is 0 or undefined, that tells us that we do have these relative extrema. Okay, they go hand in hand. Maxes and mins occur when the derivative is 0 or undefined. When the derivative is 0 or undefined, we have maxes and mins. And now we're going to put another name to it. And this name is going to be called, it's critical number. Okay, critical number, next to this, I want you to write x values. Because a critical number is always an x value. It tells me where the max and min is. The y value, though, is the max or min, technically. So it says let f be defined at c. This just means we have a function and there's at least one point. If the derivative is equal to 0, or if the derivative is undefined, then that means we have a critical number. Yeah?
So does that mean if you have a relative, if you take the derivative of a relative extremum, would you automatically have a critical number?
Yeah. They go back and forth, and that's what this theorem says, actually. Relative extrema only occur at critical numbers. So if you have a max or a min, that's happening at a critical number. The x value is the critical number. So critical numbers, extrema, maxes and mins, derivative 0, derivative undefined, they all go back and forth. Okay? This theorem doesn't get a special name, so we're not going to do a theorem write-up on it. All right? Although it's really just a definition, and I want you to understand how it relates to critical numbers. All right, so let's look at this next part. It says locate the absolute extrema on the interval. Now, without calculus, can you tell me how we could do this problem? Maybe using our calculator?
Plug it in. And
You could plug it in and do what?
then
And graph it? And just see, oh, hey, in our old calculator, we'd do second trace max or min. On the TI-89, you know, it looks a little bit different, but just if you remember second trace max or min, we do that. Now, in calculus, this is something I would expect you to be able to do without a calculator. Okay, so unless you are really good at graphing polynomials and know how to graph polynomials by hand, you know, you're kind of stuck on this problem. And even so, we never had you guys in pre-calculus find out where the maxes and mins were without a calculator. That was something you always had a calculator for. So our first step in calculus is going to be to do a calculus step, which is find the derivative. And so this part I'm going to go by quickly because you guys are derivative experts at this point. So this would be 12x cubed minus 12x squared. Okay. The second step is to figure out, okay, where is the derivative undefined or 0, right? In other words, find our critical numbers, okay? So what I like to do is check for undefined first. A lot of times there is no numbers that we get from undefined. But I like to check it first so that we don't forget it. So tell me, where is 12x cubed minus 12x squared undefined? Are there any x values that when I plug them in, I don't get a y value in return, and in fact, I get like an error, if you think of it that way? What are the types of things we do in math that give us errors? Divide by 0 is a big one. That's the one we're going to use mostly. Okay, taking square roots of negatives, taking log of negatives. Those are other things that we talk about when we're talking about undefined. Dividing by 0 is going to be a big one. So is there any chance of me dividing by 0 here? No. This thing, in fact, is never undefined. If you think about it as a graph, this is a polynomial. A polynomial is just a smooth curve. It goes on forever. It's never undefined. Its domain is all real numbers, because you can plug in any number you want. So I checked the undefined. The 0, though, this is going to be more algebra. So we're going to set 12x cubed minus 12x squared equal to 0, and we're going to solve for x. This is going to give us our critical numbers. Critical numbers are the x values. So what would be a good first step to solve for x here? Okay, I could add 12x squared, but I might lose some solutions that way. I like the fact that it equals 0, so I'm going to do what you guys are telling me. I'm going to factor out 12x squared. and that's going to give me x minus 1 equals 0. And then from here, I can, set, this is just an algebra step at this point, set each factor equal to 0, solve for x, so you get x equals 0, x equals 1. These are your critical numbers. These are telling you where you have a relative max or min. Now, I don't know if this is going to be my absolute max or min, but it's a possibility. The directions say locate the absolute extrema, but if I know where my relative extrema are, I can at least, I can go forward from there. So this is where I have relative extrema. Thinking back, I'm going to go back really quick to this problem right here, very first one we did. The minimum occurred in the middle somewhere, but the maximum occurred at the end point. And that can happen, and that will happen a lot of the time. So what we need to do here is we need to also, we need to check the end points as well. Okay? So this is what we're going to consider our end points. All right? So if we kind of go like this, I'm going to consider x equals -1, and I'm going to consider x equals 2. Okay? We're going to plug these numbers. By these numbers, I mean critical numbers and I. What does I stand for? Interval, the endpoints. Okay, we're going to plug these numbers into f of x. And then our last step is going to be to determine absolute extrema. And hopefully you are not writing as big as I am. I kind of ran out of room. Okay, so I'm going to erase over here where I've written my little cheat notes. We found the derivative, because this is what we're going to do every time the directions are locate the absolute extrema. Find the derivative, we figure out where's the derivative undefined or 0. These are our critical numbers. These are our relative extrema. Now what we're going to do is kind of like a test. Okay, so I have 0 and 1 that I found. For those of you, let me make sure everybody, where did I get these last two numbers? From the interval right there. Those are the two x values. It's saying we start at x equals -1, we go until x equals 2. You have to consider the endpoints. Those could be your absolute max or min. Okay, now number 4, I'm going to show you how to do this, okay? I just need a little bit more room. All right, so let's think of it this way. If this is telling me where, right, all of these are where we might have absolute maxes or mins, what do I need in order to find out what is the absolute max or min? Not the x values, the y values. Where do we find the y values? The original equation. Okay, this is step 3. So this is what we're going to do. We're going to find f of 0. We're going to find f of 1. We're going to find f of -1. And we're going to find f of 2. Okay. These x values, 2 of them were from critical numbers. 2 of them were from the interval. There's no set number. A lot of times you could only have one number to plug in. You could have 16. And what we're looking for is points or values. Whatever I get over here, the lowest number is going to be my absolute min. The highest number is going to be my absolute max. So it's kind of almost like a test. All right? So 0 is easy to plug in. Maybe you've already done it. What's f of 0? When you plug 0 in for x, the whole thing is 0. Okay, so I want to show you something. This represents the point 0, 0 on my graph. My original function has 0, 0, and it is either an absolute min or max. It's one of the two. It's possibly it's definitely a relative min or max. It might be an absolute min or max. We're going to have to look at these other values to know. Okay, well, what happens when you plug in 1? Yeah, 1 to the 4th is 1 times 3. You know, you do that computation, you get negative 1. Okay, I'm not going to spend a lot of time on the number crunching here. So if I had no other numbers to pick from, which one of these is winning in absolute max? Yeah, 0, 0, or you could say f of 0, and it looks like this one's my absolute min. But I do have 2 more to pick from, so I need to go through those. Okay, plugging in a negative 1. Anybody already do that one? 7 or negative 7? It is positive 7. And so this represents the point negative 1, 7. And then what do you get when you do 2? 16 is correct. So that's the point 2, 16. So what these, again, these points are either going to be my absolute max and min is one of those 4 points. So all you got to do is pick out which one is the highest, which one's the lowest. All right, so if you notice 16, that was the highest. Negative 1, that was the lowest. Okay, so here's what I'm going to do. I'm going to write my answer nice and neat. The absolute max is happening at 216, and the absolute min is happening at 1, negative 1. And this is your final answer. So the real work here is coming up with these x values to plug in, our critical numbers. That's really where most of the work comes into play. Any questions before we do another one? Okay, so let's look at the next one. First step, what is it? Find the derivative, f prime of x. So that's going to give me a 2 minus 2/3 times 3, that's 2. And what's my exponent? Negative 1/3. This is why we practiced derivatives a whole bunch before we got to this part. You got to be really good at derivatives. If you mess up here, the whole thing's toast. You can't do it. All right. So remember, there were 2 things we needed to check: undefined and 0. One thing though that may help is let me rewrite this to what it really is. I haven't been requiring you to simplify and rewrite because there hasn't really been a need. But on a problem like this, it may not be obvious, you know, when we have our answer written this way, but when our derivative is written this way, it should now be obvious that this derivative is undefined at what x value? 0. When x is 0, you are going to divide by 0, and that's not good. So this is one of my critical numbers. All right, how do I find my other critical numbers? What do I need to do before I solve for x? Set my derivative equal to 0. So we got to think. When is my derivative undefined? We found that. Now, when is my derivative equal to 0? One little tiny step I think makes this easier, and that is to add this term over to the other side. Now, if you just think about this for a minute, the answer jumps out at you. It won't on every problem, but on this one, 2 equals 2 divided by something. What must x equal? 1. Look, 2 is equal to 2. This whole thing down here must equal 1, which means x must equal 1. Now, if it's not obvious, I'm going to go through this quickly. What you could do is you could cross multiply. You could divide. That makes 1, and then you could cube both sides. Okay, either way, you're going to get x equals 1. And this is all algebra stuff. All right, so we have x equals 0. We have x equals 1. Okay, we need to plug those in to the original function. What else do we need to plug into the original function? Yeah, these 2. Don't forget those 2. F of negative 1, f of 3. If you're like, I think I might forget those, well then maybe that's where you start. You just at the very beginning, excuse me, at the very beginning, plug in -1 and plug in 30. Okay, so let's go through these again. Plugging in 0, super easy, and we're done with derivative. Okay, we don't want the derivative. We want the original function. We're talking about maxes and mins. So if I plug in 0 on the original graph, what do I get? 0. So that means the point 0, 0 is on my graph, and it's a relative max or min. I don't know yet if it's an absolute max or min. Okay, what about when you plug in 1? For those of you that are like, I don't know how they're doing this so fast. Look, 1 to any power is 1. So really what they're doing is they're just ignoring the x's. They're just saying 2 minus 3, and that's -1.
You put it in the original equation.
You put it back in the original equation. Yes. Okay, when you plug in -1, you get -2, and then -1 to the 2/3 power. What's -1 to the 2/3 power? Yeah, it's 1. The 2 on top means square it. I don't even care what the cube root part does. If you square -1, you have +1. So that ends up being -5. All right, and now for the weird one. Okay, so follow me on this. If you plug in 3, okay, I'm going to do my work down here. 2 times 3, that's 6, minus 3. And what I'm going to do is I'm going to rewrite x to the 2/3. Remember, x is now 3. And I'm going to do a 2 and a 3 here. That's what that means. So we could even scratch this out and write 9. All right. The cube root of 9 is not a whole number. So we're going to have to estimate here. What is a cube root? We do know. We know that the cube root of 8 is 2. So what do you think the cube root of 9 is if you just estimate it? It's probably just barely bigger than 2. Not a whole lot, though. Just a little bit. Cube root of 8 is 2. Cube root of 9, I mean, because you got to go all the way to the cube root of 27 to get to 3. So we're way closer to 2 than 3. So 6 minus 3 times 2.1. I want you just to hang with me here with your brain and just think, what is that about? 0. It's really close to 0, so it's a really small number. Is it positive or negative? Negative. So I'm just going to say -0.1, and this is a rough estimation. Okay? In our problem here, does it even matter? Why does it not matter? Yeah, because when you're going through and trying to figure out your max and your min, -5 is definitely the min, 0 is definitely the max. This part didn't matter at all. And typically when you get a really weird computation, it's because it's not your answer. All right? So the way we would write our final answer is to do absolute max, that's occurring at the point 0, 0, and our absolute min, that's occurring at the point -1, -5. And if you did want to check these, you could definitely do that in your calculator. Okay? You could just graph it and then just locate these points on the graph or on the table or something. All right. Turn it over to the next page, and I want you to scroll down to the very bottom. Well, I'm scrolling down. You're just moving your eyes. All right. So it says finding absolute extrema. What this really is just a recap of what we've done. It says let f be continuous. Remember, that's important. Let's have a closed interval. That's important. We can't do this if we don't have those two things. It says find the critical numbers of f. All right, remember critical numbers, that was when our derivative was equal to 0 or our derivative was undefined. We evaluate the critical numbers. We evaluate at the endpoints, and then the least of these is the minimum, the greatest is the maximum. So this is just a little bit more detailed. This is what I was saying, but now it's typed out. All right. I'm going to see how far. I want you just to totally just scratch out that function. And I want you in its place to write f of x equals sine x. Because this one, it kind of goes from like 0 to 90, and we need to do a trig one that's a little bit easier. Okay, so you tell me, what's the first step? Find the derivative. What's the derivative of sine x? Cosine x. Okay, now what do we do? So is this derivative undefined anywhere? Yeah. It's just a periodic, it's never going to be undefined, okay? So not undefined. You definitely know that cosine x could equal 0. So what are my x values in this closed interval to where cosine of x is equal to 0?
0 and 2.
Okay, let's think about trig-wise. What do we have at our disposal? We have the trig hand trick, or the right triangles, but 0, if you know about the OIO chart. But I'm going to tell you, after teaching trig for many years, I think when you get to these, the easiest way to do this is to think about a graph. Okay, this is what one cycle, and I kind of went beyond, but just to show you. This is what one cycle of cosine looks like. It starts at a peak, it goes down, it comes back up to the peak to end at 2 pi. So if I'm saying, where is cosine x equal to 0, what I'm asking you is, what are these values? 90 and 270, and in radians we write that as
Pi over 2 and 3 pi over 4.
close. Pi over 2 and 3 pi over 2. Okay, I really think this is the easiest way. What if this was cosine x equals -1? What would your x value be? It'd be pi. Okay, you know what the parent functions look like. Use that to your advantage. So these are my two critical numbers. So I need to figure out, okay, what is f of pi over 2? I need to find what is f of 3 pi over 2. What else do I need to plug into f? 0 and 2 pi. And remember, the original function was sine. So maybe we need to graph sine over here. Because these are all what we call quadrantal angles. So at 90 degrees, and maybe it even helps you to, 90, 180, 270, 360, or pi over 2 pi, 3 pi over 2, 2 pi. What is sine? This one was sine, and over here was cosine. What is sine of 90? Yeah, it goes up to 1, it goes down to -1, and the middle 0. So that's 1. Okay, what's sine of 3 pi over 2? -1. What's sine of 0? And 2 pi? 0. So when we're looking for our max and our min, remember we're just picking out what's the highest value, what's the lowest value. So here's my max, here's my min. So I have an absolute max at pi over 2, comma 1, and I have an absolute min at 3 pi over 2, -1. And keep in mind, we stayed in our interval the whole time. That's why I don't have any negative angles. Remember how messy negative angles were last year? You really don't have to do that here because pretty much every time your interval is going to be 0 to 2 pi. I never really see it any other way. Okay, and this is a very simple trig one. This is as easy as a trig one gets. So some of them are going to be a little bit harder. Okay, but the one I had there was like the hardest it could possibly be. So I wanted to try an easy one first. All right, we're going to continue this tomorrow. You have homework. It's on your timeline, so make sure you do that.